Let me welcome everybody for the next lecture, which was devoted to commemorate the three Polish mathematicians who wrote Enigma code. As you know, in 2008, at Faculty of Mathematics and Computer Science, we decided to establish such a series of lectures. Let me thank you for the support of university, who was represented by President of the University, Professor Banaszek, and for support for our faculty, who is represented here by the Dean, Professor Rejewskiego. And as you know, this series of lectures is given. Well, there were a few lectures which were given by historian and witness of these events, like a few years back, we had here Sir John Dermot Turing, whose uncle Alan Turing was involved in the breaking Enigma code as well. But most of them were given by the leading experts in computer science. And today's speaker is certainly qualified as a leading expert of it. As a matter of fact, I think that Professor Nati is one of the most innovative scientists I have ever met. So his new ideas open new avenues of research in both computer science, computational biology, and mathematics. And well, of course, he was awarded many honors and awards like Honan Prize, Dijkstra Prize, Rothschild Prize, and so on. But he is also a person we used to call a Renaissance man. So I remember our discussion on philosophy, politics, history, literature, religion, and of course maths. And maths is a sort of special area. So maths is the area when most of the time we could agree on some sort of common points. But anyhow, so today's lecture will be about connections between, surprising connection between computational complexity and additive combinatorics.
Thank you very much, Tomek, for the kind introduction. First of all, those of you who haven't heard me speak before, I'm always in favor of interaction. So if there is any questions or comment or anything that you have to say, don't wait politely till the end, just barge in and say it. The more interactive, the better. And so perhaps I thought there is a great Jewish tradition of first, speaking about your connection to the place and the time. So there are many, but two that I should mention is that my mother was born in this country, in Łódź. And secondly, it's more related to the Polish cryptographers whose contribution we are celebrating today. So you all know about Turing, but this amazing team that worked in Bletchley Park and eventually resolved this problem and broke the Enigma. Many other great people were there, perhaps a little less famous than Turing. William Taft was there, who was one of the founders of modern combinatorics and graph theory. And another person whom you probably never heard of, his name was Joe Gillis. He was a British Jew, so after the war he immigrated to Israel and he became a professor in Weizmann Institute. And he really was a great pioneer in encouraging math for the youth in Israel. Today we have the Israeli Math Olympiad is called after him, but when I participated in these competitions, it was him. He stood there and arranged everything, and he had a math journal for high school kids, which influenced myself and everyone I know from my generation who is a mathematician. So this is the connection. Okay, so now I'll start with my talk. I tried to make the talk accessible to non-experts. So we're going to talk about technical things, but I'm not going to get into very technical things. And if you want, I can later, those of you who are interested, I can give you pointers to more concrete things and more technical discussions of things. So you all know that we have these huge problems. So my topic, one of the nice things and one of the things that fascinates me about this is where computer science and mathematics meet. In fact, if you ask me, I usually try not to say these things aloud, but I don't know where the one field ends and the other one starts. It's, for me, a whole range of questions and ideas. For me, it's theoretical computer science is one of the most beautiful and exciting parts of mathematics. But what I'm going to tell you today, really the questions arose in two different contexts, but as I hope to convey to you, they're really the same thing. It's taking two different perspectives of the same subject. The fact that it's the same subject is not obvious. I'll try to illustrate and explain. And it really opens the gate to lots of developments, which I hope will. So you all know, I think, about P and NP and the fact that we have very hard time proving that various lots of all the problems which are NP hard in the thousands, we cannot solve them efficiently. We don't know how to do this, and this seems to require still a lot of work. You know, we mathematicians, we don't get scared with this. It took us 350 years to solve Fermat. We have time. There is really no problem there. And yet, you know, one of the key ideas in meta-mathematics, in how you approach very difficult problems, is sometimes you look for ways which really somehow go around the problem, and eventually perhaps they show you the way to and how to solve it. So one such approach, which I don't want to get into the history, but let me mention just the name of NDR, who he wrote the first concrete papers that have made important contribution. This is what's called communication complexity. And while I'm at it, I will add that there is I think from 1997, about a book by Kushilevitz and his son, dedicated to this area, which, although it's only a quarter century old, it still makes for a very good reading. So if you get your hands on this book, highly recommended, very well written. So what is it? They discuss, so let me just say, I'm going to talk about this for a while, then I'm going to discuss some number theory questions, editing and combinatorics, and then you will see why the two things are the same and what the potential is for growth here. So what is communication complexity? Let's say what are Yao's papers about, what is Kushilevitz and Nissan book about? So they describe the following scenario. The idea is, so since this going around the approach, since we don't know how to prove that certain computational challenges are difficult, we're trying to extract one ingredient from it. So this is considering how much communication is needed in order to solve certain problems. Why is it relevant, let's say, to questions like P and NP? Because you can also think of the two players are yourself. They're the one computer who works on the problem in the past and in the present. So they have to communicate things to each other. And this is trying to capture that you need a lot of communication. So it's described as a two-player game. There is a matrix. Usually a matrix with entry 0 is 1 and is already interesting and rich enough. So the two players study this matrix together and decide with themselves how to approach the problem. And then when they are ready, there is a referee who separates them and tells one of them an index I, an index of a row, but the other one doesn't hear it. and tell the other players an index of a column, J. And the goal now is to, let's say this matrix is A, so they need to tell what AJ is. Now, and they want to do this with the least possible communication. Of course, a very trivial way to do this, which can always be the role player can tell what I is. This matrix is, let's say, this means that by sending log n bits, the game is over. This is a trivial solution. And sometimes, in fact, often, for most matrices, as you can not, it's not difficult to show, for most matrices, there's nothing better than you can do. But there are lots of other problems. There are lots of very interesting matrices A or some functions like this. You can think of a matrix also as a function of I and J, where more efficient things can be done. And then the main objective of this area is, given such a function or such a matrix, to determine what is the best algorithm. And as usual, the most difficult part is to prove lower bounds, to show that for certain cases, it requires a lot of communication. So let me show you the simplest type of such a lower bound. And then we will be able to go on with this and continue to other problems. So let's describe a run of such a protocol in two different ways. So one is a tree. So let's say the role player goes now, and let's say he sends either a 0 or a 1, and then things can evolve. What the column, let's say we go bit by bit. The role player sends bit by bit. Okay, what does it mean? So how do we interpret this? So what could it mean? I mean, we were not there when they communicated, when they talked to each other and decided what to go, but we can understand what's going on. They have agreed that for this set of rows, and I do it like this just for convenience. I draw it as if the top rows are for 0, but there is some sort of set of the rows which, if I is in that set, then I say the role player, I said 0, and otherwise I say 1. And now the next term is due to the column player. And again, he can send a 0 or 1. And how do we understand this? Well, let's say we are in this case, let's say we follow this part of the, and let's say we can also decide, let us say that this is the choice. So in the initial agreement, they said, okay, if you send me 0, then I'll send you 0, 1, according to whether I'm here or there. And we continue like this. Or there will be something small which, if it makes you, if you feel more comfortable with it, think of it as plus minus 1. It's the same thing. You'll see in a minute why I'm making this comment. How does the game end? What happens in the leaves of this computational queue? In the leaves, we know that the outcome Aij, here we have Aij 0, here perhaps we are in Aij equals 1. How does this happen? As the game proceeds, what happens? What happens in this case? In this case, we know that really we're dealing only with this submatrix. And when can we stop? So we're going to chop this matrix into smaller and smaller pieces. We can stop only when this submatrix is all the same thing, either all zeros or all ones. Then and only then can we stop. Before that, this is impossible. We still don't know the answer. So in particular, what we have, if the height of this tree is h, this is the communication complexity, that's how many bits we send. There are at most 2 to the h leaves here. And this means that, so if the communication complexity of A is at most h, this means there is a protocol that does it always with at most h bits of communication. This means that A is the sum of at most 2 to the H that we call monochromatic blocks. Now let me remind you something small of linear algebra. A block of all pluses or a block of all minuses is a matrix of rank 1. So this means that I've expressed A as a sum of at most 2 to the H matrices of rank 1. And rank is sub-additive, and consequently, the rank of A is at most 2 to the H. So reversing this, putting this thing, we conclude that the communication complexity of A is at least log base 2 of the rank of A. So now you saw your first lower bound in communication complexity. We're using linear algebra, and we found a way. So think about it. This says this is a lower bound of the communication complexity. This says you cannot solve this problem for the particular matrix A too fast. And what's the quantity? The quantity is log base 2 of the rank. By the way, this is an aside. We're not going to discuss it, although this is a fascinating subject in its own right. There's a famous conjecture due to Novas and Sachs, the log rank conjecture, which says there exists a C such that the communication complexity of A is equals to log base 2 of the rank of A to the power C. This is still wide open. Fascinating conjecture, which I'm just mentioning it for. Okay, very good. So we already have one thing. We have one technique in order to prove hardness or to prove the lower bound of the communication complexity. We have a conjecture. What else can we say here? There is lots of different methods and techniques that people have introduced. Let me just mention. I'm not going to. There is an issue. So, in other words, let me be more concrete. You're looking at such a matrix and you're asking yourself, what is it that makes that particular question associated with this matrix difficult? So now we know one reason why it could be, because perhaps it has a high rank. There is also an issue, there's tons, I mean, the book is and you said that there is discrepancy. If the zeros and ones are somehow spread out fairly uniformly, that's a reason. I'm not going to go into any, just to give you an idea. There is also, in addition, lots of wonderful things. You can use randomness, so the two-player can use random bits. Somehow, there is even quantum. You can use the randomness that comes from quantum mechanics. And so it's a whole field, beautiful things, and it's connected to lots of beautiful mathematics and computer science. So I've given you, really very quick introduction to this area. Okay. But if you know this, there are certain rules. If you go to a math talk and you fall asleep, and you wake up at the end and you still want to show that, no, I didn't sleep. Well, what do you think? I was listening the whole time. Can you at least ask a question? So here is one, if you have such a thing, you can always ask when you wake up at the end, so what happens if there is more than two players? That's what happens in higher dimension? What happens over the complex numbers? There are safe questions like this to ask. So I'm going to ask this while I'm awake. What happens with more players? So there is bad news and good news. The bad news is that essentially all the machinery that you will find in this beautiful book of Koshilevich and Lisan, all of it fails, completely kaput. It's all going through the window. Simply doesn't occur. And so what I want to first show you why ideas like this rank and partitioning into uniform blocks or monochromatic blocks, why this fails and where we are now. We are really I mean, the situation is not easy at all. And this is where our story begins. So let's start to think about it just with 3 players. Okay, the first thing that you have to ask yourself when you want to consider what happens with more than 2 players is how information is given to you. There are more than 2 answers, but 2 main answers, one which is less interesting. And so, in a way, you would think, the obvious thing to ask is that here we had an array of zeros and ones, and we gave them information, and we asked what's in the corresponding entry in the matrix. A reasonable thing to do, that would be certainly a reasonable thought, is that now we have an n by n by n, or an array, a 3-dimensional array of zeros and ones. And we give them each a coordinate, and we ask, there is a corresponding spot in this array, and we ask what's there, 0 or 1. This is called a number in the hand problem. So player one gets a note and says I, and so on. But really the more interesting and the deeper and the more challenging problem is what's called number on the forehead. NOH, number on the forehead model. So, which means that the referee now, after they look at this and they discuss and so on, he writes an integer on the forehead of player 1, an integer on the forehead of player 2, and an integer on the forehead of player 3. Let's say x, y, and z. We'll come to this momentarily, which means the first player knows y and z. The second player knows x and z. And the third player knows x and y. And then the question is, what is written in the x, y, z entry of this array? So let's try, remember, this was very elementary. It took us exactly 2 minutes. We said, there's a set of rows, for which this player will say 0, so a set of, and we somehow, and what happened at the end? Why? Let me tell you this part, which was completely obvious, but I want to say it in words that will help us in the new situation. Why is it that the game only ends when they breach a monochromatic block? So why is it? So let's say it always ends with the block, fine. But let's say that this point is in the block and this point is in the block. This means that the row player agreed that this row is relevant. And this means that the column player says this is still in the game. And consequently, this is also in the game. So, and you can apply the same thing here. This is a long way to say something which is completely obvious. So if this is 1 and this is 1, then this must be 1. And therefore, it's just a monochromatic block of all ones, same with zeros. What would happen here? What is the substitute of our conclusion here that the row player just partitioned the, let's say this guy, the Z guy, speaks first. And let's say he says 0. What can we conclude from this? So he knows X and Y. So there is some subset of the XY plane on which he would say 0, and in the complement, he would say 1, which means that if he spoke and said 0, this looks like a leg for breakfast, right? So if he says 0, then all we know is that in the same way that here we knew that we are in this part of the matrix, here we know that we are in this part, we call it a cylinder in this array. And the same way, so what replaces these monochromatic blocks is what we call intersections of cylinders. They are much more mysterious. We don't have mathematics that deal with them. I mean, blocks and rank and so on, that's standard linear algebra, but now we are in a completely foreign situation. So what can we say about this? Can we imitate this kind of argument? So for this, I brought this little model from home. 3 fingers, that's all I need. So you see, if this one, we terminate somewhere, and this one, and this one are in the terminal set. So it's again the case that as we speak, the set of potential places that we deal with gets smaller and smaller. And what happens if this spot, and this spot are all in the terminal set? This means that this player approved of this line, this player approved of this line, and this player approved of this line. Consequently, this one should also be the same. So in the same way that given these two guys, I know that this is in the final set. If I have this, and this, then I know that this must be in final. That's all. That's the whole weapon that we have, with which we have to go into this war, and let's see if we can survive. So the question that has received the most attention in this area is, so what is the function that we want to solve? Let's say there is some number n. So what is this array going to be? So we're going to ask the question: is x plus y plus 3 equals to n? So they publish a number n. The idea is this is what they have to. Again, the player with z on the forward can look at the other numbers and say x equals so and so much. The same trivial thing you'll find it here too, and that is a possible answer, and this is a trivial solution. But is there anything better than this? Turns out there is. I won't have time today to show you this, but I believe that much better than what we have is still possible. Okay, so let me now start talking about the second ingredient in my lecture, and this is additive combinatorics. And then we'll see how these two areas mix together and new things arise. So now I'm going to tell you a little bit about additive number theory, or additive combinatorics. So this is an area with a lot of activity, which has received a lot of attention. If you just look at how many Fields medals were given in this area, the number is really, really big. So lots of the world's best mathematicians are working in this field. And so let me give you just a quick introduction to it. The first, and is for sure that is perhaps, again, I'm not doing complete justice with the history, I don't have time to do this, but it's reasonable to say that the first theorem in this area is due to van der Waals, and he proved the following theorem. In every column of the positive integers with a constant number of columns, there must be arbitrarily long allocated progression. Okay. So if you see this for the first time, let's spend a minute thinking about this. So you take all the integers 1, 2, 3, and so on, and you assign 1 is red, 2 is blue, 3 is green, 4 is green as well, and somehow you color all, you assign a color, or if you want, this is somehow the language that combinatorialists are used to. If you want, if you partition, if this is more convenient for you, if you partition the integers into a finite number of classes, right? If you write n is S1, it's going to be S2. Then, if you have such an expression, then one of the SIs must contain arithmetic progressions of arbitrarily long length. So you give me any k, and there will be an arithmetic progression a0, a0 plus d, a0 plus 2d, up to k minus 1 times d for everything. Okay? That's the theorem. It's all very pretty, and I won't. It's still today not. I wouldn't describe it as very easy, but it's not something. It's stuff. My criterion is that stuff that you can prove in class. I don't think I ever did it, but it's something I wouldn't hesitate to bring to a good class of students. Okay. So an obvious question to ask, given this, is which of the S's, can we say anything about which of the S's has arbitrarily long arithmetic progression? So now I'm talking really complete, very, primitive, intuitive, in a very primitive and intuitive way. You would think, so don't take this too seriously. Somehow the biggest SI, whatever that means, we are going to discuss it, you expect that set to contain arbitrarily. If anything set contains it, then probably the largest of the SIs. And this is, of course, complete rubbish, because in principle, they're all infinite sets, they're all infinite countable sets, so there's no notion of largest. How do we even formulate this in a mathematically coherent way? How do we even capture this intuition in a precise way to ask? I'm not even talking about answering, but just to ask. This is in general, by the way, something which I feel is I'm critical about in math education, that people don't get encouraged to ask questions, which is, I think it's too bad, because it's a big and important art. So asking good questions is far from being a trivial thing. You really need to think a lot before you can ask a good question, but it's a very satisfying game. So this suggests a conjecture, which I can already tell you, a conjecture of Hermes and Turan, which became a theorem of similarity. I forget, I think it's like this, but there's no Hungarian, I hope you just catch me for not spelling similarity correctly. It says, so I'll first sets, so every set this would be the density version of van der Waals. The conjecture would say that every set, again, let me be informal here, of substantial density I haven't defined what this is, but must is subset of the positive integers. Must contain arbitrarily long arithmetic progression. So how exactly do we capture this? So I think everyone here is comfortable enough if I write this in the epsilon delta language. I'm not going to go any deeper than that with the math. So yes, this was a major accomplishment. Similarly, I'll tell you a few things about that. So the theorem of similarity should be consistent. It says for all epsilon positive, and for all positive integer k, there is n0 of epsilon k, such that every subset, such that for every n bigger than n0 and any subset S of 1 to n of size at least epsilon times n, the set S has a k-term arithmetic progression. So the way around these difficulties with how do you define density and so on are taken care. We are not really talking about the whole integer. We are talking about a chunk. You want 1% and arithmetic progression of length n. Yes. So take n to be a zillion. I have no idea what the number is, but if you take any subset of the numbers from 1 to zillion, whatever that number is, of at least 1%, then it will contain a 10-term arithmetic progression. This is the same thing again. So let me just say a word about this. This has had a very long and interesting history. K equals 3. K equals 3 was proved by Roth, who won the Fields Medal not only for this, for other great things that he had done. K equals 3, I actually did in class. It's not, this is quite reasonable to do. We have more than one proof for this today. Larger K already requires new ideas. Mostly the idea is ideas that similarly developed, which became crucial to all of modern combinatorics. I'll only write this is something. Is regularity lemma. Which says in rough words, which I'm not going to go any deeper into, that every large graph you can partition in a way that it looks locally between the parts like a random graph. So that's roughly what similarly is regularity lemma says. And one of the first accomplishments of Semirevi's regularity lemma was the Semirev-Ruja triangle removal lemma. Which says that, so here's what it says, just to make sure that my quantifiers are correct. For every epsilon positive, there exists delta positive, such that if in n-vertex graph is fewer than delta times n cubed triangles, it can be made triangle free by removing its most epsilon times s squared edges. Okay, so this is not a, again, I'm not going to go into any of the details here, but this, the triangle removal lemma is a consequence of cellular irregularity, which I just described in hand-waving forms. And then again, to conclude from this combinatorial statement, to conclude from it, Roth's theorem, she says that, let me, you know, if you're seeing these things for the first time, then I don't think it's very, very easy. So let me spend another minute on this. What is Roth? It's the first in this line, right? What does it say? I'm stating it separately. It's kind of, it's of course a special case of this. But let me just say this. For every positive epsilon and every large enough n, any subset of epsilon n integers in the set 1 to n must contain an arithmetic triple. So what is an arithmetic triple? A minus d, a, and a plus d. Okay. By the way, it's you know, I won't even start to get into the intricacies of this thing. You know, I've brushed off deep and beautiful and highly non-trivial mathematics, which is all fine and good. But the quantitative aspects of this are still a huge mystery. There's been great progress. Again, I won't have time to get into this. But what I mean by quantitative? The question is, for example, to be completely concrete, I give you an epsilon. What does that do now? For which end does this start to be correct? The difference is that there is still huge gaps between the upper and the lower boundary. So the quantitative aspects of this, or here, the triangle removal lemma, how does delta depend on epsilon? The gaps there are still huge. We still do not understand. But so you would think that so far I told you two separate stories. You know, I told you about communication complexity. I told you about additive combinatorics, all beautiful and nice mathematics, but what does the two things have to do with each other? So now I want to close this cycle and show you how the two things come together and turn out to be really talking about essentially the same problem. So again, in the search of the local versions of this, what I mean by local version? Remember, when I started, I spoke about van der Waals theorem. In every coloring of integers with a constant number of colors, there is a there are monochromatic, arbitrarily large, long monochromatic arithmetic progressions. And we said, okay, we expect which color is going to have these things. We expect the most abundant color to have it. And then we said, okay, so why do we talk about constant number of colors, and we have trouble deciding what it really means, the most abundant color? Let's talk about one set. And then how do we capture the fact that it's large? By making assumptions such as this. We're really going to take the whole thing into the finite world and just say that on an interval of 1 to n, it occupies at least an epsilon fraction of the number. So we already have the tools to formulate and to ask such questions. So I think it's again, Rejewskiego, I'm not 100% sure who asked this question, and this was eventually answered by Aita and Semeredi. Coleman's formula. Coleman's theorem. So to Coleman, now they did the theorem. Okay, so I need, we are looking now for something two-dimensional, which is in the spirit of, let's say, an arithmetic triplet or something like this. And so perhaps now you'll start seeing some connection with the so a corner, so if S now is a subset of 1 to n cos 1 to n. Now it's a subset of the integer grid. It's a set of lattice points. A corner is a set of 3 points xy, x plus d, y, and x comma y plus d. So the way it looks in here, it's something like this. This guy, and this guy. Okay. So what the Aita summary the Kohler theorem says that for every positive epsilon and every large enough and every subset S of 1 to n cos 1 to n of size at least epsilon n squared must contain a common. So now the two stories come together. You remember that we spoke about, so how do the two stories come together? So first of all, I didn't give proper credit, so I should. The whole area of communication complexity with more than 2 players was started by Chandra Frost and Lipton, and they already understood that there is a connection between these problems and additive combinatorics, but the toolbox that they had at the time was, this is I think 83, so 40 years ago. The toolbox that they had at the time was rather limited, and they only more recently, so I should at least mention my ex-student, Adi Schreiber, who really dragged me into this area. So Adi's idea was that this connection between communication complexity and additive combinatorics is not being exhausted. There is still a lot to do there, and his philosophy says that we are quite good in algorithmic thought. So we can think that let's take. I still owe you an explanation how exactly the connection is made, which I'll do momentarily. But if the two areas are connected, we can think about solving, for example, the sum problem. You remember the number on the forehead, and the question is x plus y plus z equals n, right? That's the question that they have to answer. So there is a hyperplane x plus y plus z, an affine hyperplane x plus y plus z equals n, and they have to decide if with the x, y, and z that they have written on their foreheads, if this triple x, y, z lies on this hyperplane or not. So Schreibman's idea was that, let's think about it in algorithmic terms. In these additive combinatorics, there is no algorithm, but we are good in developing one. Perhaps we can make some progress there. And the answer is, well, so initially it was work with Noga alone. He made progress on this Chandra, Frost, and Newton, then he worked with me. And in particular, this is not such a huge improvement, but we managed to, again, the quantitative questions are always difficult. What is the relation, the quantitative part? Given epsilon, how large does n have to be in order for this to hold? Again, the bounds are still very weak, and my work with Adi has improved this, but still, I believe that much more can be done. So I now owe you an explanation, really to nail down the connection between these two problems. So let me remind you what we had before. You remember we said in two players, it's the easy situation, it's just partitioning somehow a matrix of pluses and minuses into blocks, monochromatic blocks. Here the situation is difficult, and the only thing that we have was this thing that I showed you with the fingers. That if you look at the tree that you calculate, what happens in the leaves? Which subset of the n by n cube do we have? No, it's not the same n. The array, the three-dimensional array that we have, which part? So we already the only condition that we have, the only thing that we have to work with is that if this point is in the set, this point is in the set, this point is in the set, then this must be in the same set either. But now we're talking about x plus y plus z equals n. So these 3 points are really on a plane, which tells us that these 3 edges have the same length. So now I'm not giving full details, but you can start seeing how the structure of the color starts to show up, and we're able to improve the best known bound for the colors problem. Again, not a huge improvement, and I believe that much more can be done. But I've really told you a lot of things, and I don't know how much of it you are able to swallow in this short amount of time. So let me just, I'm a great fan of, this is why I became a combinatorialist and a computer scientist. I really like simple mathematics. The objects should be simple for me to like them. And I'm fine and I'm very appreciative of the fact that I have colleagues who like to work with complicated objects. I like to work with simple objects. The point is, let me tell you again, the big problem, I've been thinking about this problem for several years now. We haven't solved it yet, and I keep thinking about this more or less day and night. It's a problem that you can tell to your cousin, whether the cousin is a mathematician or not, or a truck driver or school teacher. This is the problem. So think about it when you are on the way. It's a game between three players. One of them, and let's even forget N. One of them has X on their forehead, the other one has Y, the third has Z, and they have to communicate and just decide if X plus Y equals Z. You just complement to replace Z by N minus Z. That's all. Just the fact that you can even do something non-trivial with this is not very difficult. I don't have time for this, but it's not. With another 10 minutes, I can show you the whole thing beginning to end, how to do this. I don't think I have time. You know what? I'll do it. I still have 4 minutes. I can do it in 4 minutes. Yes, I'm good with the time. Okay. Sure. Okay. So I'll show you this. But I believe that much better than this can be done. So let me show you how we do better. But this, again, I will not drag you into the technical details, but the construction eventually is quite simple. And really, I must, again, give credit to Adi Schreiber, because this is, to me, this is why I was so fascinated by his idea that a priori, why should there be any connection between algorithmic thought and additive number theory? And he says, just because it's the same problem. So now think about, let the algorithms person show themselves and solve the problem. So this is eventually how, in my work with Schreibman, we gave a better method to this. And again, I'm not going to drag you through the technical calculations, which are not difficult. But it's really very, very simple. We have to, let's say we are solving X plus Y equals to Z, yes or no. And we know that X, Y, and Z are between 0 and, let's say, big N. Okay, so X plus Y plus Z equals N, so I complement, I replace Z by N minus Z. It's the same problem. This is perhaps a bit more, there's no external constants. Okay, so here is a very nice observation, which I must say I've known this for several years now, and I feel it's still a riddle, it's still a mystery. Had we have to solve a question like this, not with integers, but with vectors, it's actually very easy. I'll show you in a minute why. Which I find fascinating and confusing. How could it be? Adding vectors, as you'll see in a minute, is a triviality. Adding integers, we don't know. Does it stand to reason? That's what it is. So what do I mean exactly by vectors? There are vectors. And let's say the coordinates in X and Y go between, let's say, 1 and Q, okay? And Z, it's between, or 0 to Q, and then Z is between 0 and 2Q. Then so this means that N is roughly Q to the D. So we are writing numbers in base Q, and the numbers are D-digit number, okay? So this is the setup. We will have to determine what are the good Q and D, but at the moment we leave this unspecified. So how do we check this? Well, that's very simple. This is if X, Y, and Z are vectors, then this holds if and only Z minus 2X GOM squared plus Z minus 2Y GOM squared is 4 times x minus y norm squared. This is just the quadrilateral equation. So I mean, if you spend, this is really just first year linear algebra analysis. It really says that 0/2, where instead of looking at this equation like this, we're asking if the vector 0/2 is exactly the midpoint of x and y. This is very easy to verify. It takes a minute, but really just a minute. You all know how to do this calculation. What's the big advantage? The big advantage is that there are two advantages. These are all L2. Player Y knows this number because all you need is to know Z and X, and he knows. Player X knows this number. Again, you only need to know the vector Z and the vector Y, and he knows them. And player Z knows how to calculate. The additional thing is that these are very short numbers. These are numbers, they are no longer vectors. This is on the order, the numbers that we're talking about is on the orders of dq squared, which is essentially logarithmic in view of this. Okay? So this is essentially all we do. What's wrong with this? Where have I cheated you? I've cheated you because in integers there is carry. So the additional ingredient that we eventually says is that Z says which the carry bits are, in which positions in the D in the D coordinates do we do a carry, and then we can again check this equality perfectly. And so we need this log of this in order to send these numbers. He needs something like D bits in order to tell where the carry bits are. Now there is a little calculation to do. What are the optimal Q and D? And when you do this, you get that instead of let's say they're all in L big integers, so we could solve it in the trivial way by Z telling what X is, so by sending N bits. This is something like exponential root. And this is perhaps not what you are used to think about when you wake up in the morning, but there are people among you who do. And to convince yourself, this is for combinatorics, it's bed and breakfast or bread and cheese. I don't know. For others, perhaps it takes a minute to calculate. If you want to convince yourself about this, take log in both sides. So here when you take the log, you get log of n. Here when you take the log, you take square root of log n. So this is much smaller than this. And if you do the calculation correctly, which is, I've told you everything that you need in order to carry this out, you come to the conclusion that this is really a more efficient way to decide addition. But I really believe that much better than this can be done. I've been thinking about for 3 years or so, and I will not give up. But if any one of you has ideas about this, then go ahead, think about it. This is, to me, this is a fascinating problem, that you can, as I said, explain to an arbitrary person with only minimal mathematical background, and we still don't know how to answer. So with this, I think I'll stop. Thank you very much.
Ask what that's the case of phone frames.
Yeah, you would like to. You asked me.
Okay.
I don't know. I actually don't.
So it's very similar to this parent stuff.
Okay. Now, Tomek is talking experts. There is a standard construction which has been there from the 40s. In this whole area of additive combinatorics due to Berend, which is actually quite simple. Again, I'm reusing the criterion that I already used today. I showed Berend's construction in class. In an hour you cover this. So this is a construction of a large by now, I think you should be able to appreciate it's a large set of integers from 1 to n, which contains no arithmetic triplet. I can even tell you the basic idea. The basic idea is that if you have a sphere and a line in the space, in free space, in any space, sorry. If you have a sphere in any space and a line in that space, the line can intersect the sphere at most twice. And 2 is less than 3. This is why this gives you a no three-term arithmetic progression. It's really very, very simple, the Barron construction. So the interesting point is that our improvement with Schreibman of the corners is the first construction which beats the Barron construction. The beating is very mild. It's not a huge difference. But yeah.
But my question is, so there was this recent result of Kelly-Mecca. So they show that basically that Barron construction is optimal for rods. So don't you think that maybe there is some sort of...
You're right. This is something that occurred to me, and I haven't checked it yet, but it's maybe, definitely...
Maybe
perhaps this Ragumeka result changes the scene. I haven't thought about this enough. Yeah, definitely. It should definitely be checked.
Because you think that it's not optimal, so maybe it's almost optimal up to the power block.
Possible.
Yes, please.
I have one more general question, because I understand that this is about communication of bits,
right?
0, 1. But you also put a word which caught my attention, which is quantum.
Right.
So could you comment on
yes. So
qubit communication?
So yeah. So about this. You see, what happens when you want to introduce randomness into the game? Any kind of randomness. First of all, so it's a whole subject with beautiful results about this. First question is, where do you generate? I mean, what kind of randomness do you generate, and where do you get it? So, for example, you could say, okay, we give each player a coin, and a player flips the coins, and that's one coin. And another thing is that someone external flips coins which both players can see. So it's a result of Newman, who showed that the two things are equivalent. And then you can say, okay, so what happens if I allow them to use the randomness that comes from quantum computation, or from quantum mechanics? And that too sometimes can do better things. So all these things are investigated. This is all, but again, the main thing is what happens as we go from 2 players to more, and there is more players. So, for example, we know that had we been able to understand communication complexity with something like log n, this is coming back to your questions about 3 and 4, then we're already starting to touch the holy grail of P and NP and so on and so forth. So it comes in all sorts of types and variations. There's also quantum. I know less about doing communication complexity under the quantum model, but this has been looked into quite deeply.
More questions or comments? Yes.
I'd like to ask you, in the near future, what is your prediction of which part of pure mathematics will be applied to computer science, and therefore with what kind of courses we should offer our students in coming years?
See this?
Sorry, Krzysztof is a very good topologist. So.
No.
You're doing topology as well.
Yeah. So you're talking to the right.
Just hints you need to go in the right direction.
You're talking to the right person. So I've been doing all sorts of combinatorial approaches to topology, such as random nodes, random simplification complexes. It's all fascinating. I still consider myself a a novice. Each time I get surprised by how deep topology is, so I'm not telling myself any stories. I just bite the very, but sure. So ideas. The answer to your first question is everything. You know, to me there is really no distinction.
No limits.
Really no distinction. But of course, you know, we were unable to learn everything. But you see, you know, I'll give you a different example which I saw firsthand. Let's talk about probability. I think today, no one in their right mind would think of, you know, educating computer scientists without teaching them probability. I did my undergraduate in the Technical in Haifa, which is a very good school, and no one even, of course, probability wasn't required. And the teacher who taught this wasn't such, I mean, it was a very nice person, but wasn't a very good teacher. So the consensus among the students was, let's not take this class. Why? And luckily, by the time I got to postdoc, I understood that this was a bad mistake, and I went in UCLA and sat in classes. And so by now, the fact that probability theory, discrete mathematics, theoretical computer science, you know, they cannot, you know, coming back to understanding the impact of quantum physics on all of computation. You know, now people talk the whole time about post-quantum cryptography. How will we be able to send, I mean, okay, we're in the right place to discuss it. You know, cryptographically secure messages in a world where the attackers have quantum computing. And there are many things. So basically, RSA and so on are based on the assumption that we are unable to factor large numbers, which, of course, with quantum computers, we can. So to me, there is really no barrier. You know, the more mathematics you know and the stronger connections that you make, this is just to the better. No question.
Maybe I should ask. I should ask that Nati, for instance, uses topology to construct error-correcting codes and so on. So this was one of his inventions, or many, out of many. So
may I ask one more question, which bothers me a lot recently? You know, about artificial intelligence developing so quickly. So from your personal point of view, it's more interesting or scary?
Both. It's both. No, I think it's, yeah, we discussed it on the right here. I'm scared of this. I think it's the first time in human history that we have such an amazing technological development that no one understands. It's really scary. It's at the same time, you look at what these machines do. It's amazing. Is too small a word to describe it.
Any other scary question or perspectives? If not, let me thank our speakers.